Okay, so here we are, Unit 8 still, electric charge and electric force, and we are on Part 3, which would be conductors and insulators, or dielectrics. And as you can see, there's a beautiful picture of a conductor, which I'm hoping you realize really has nothing to do with this, right? These are words of similar meanings, similar words with different meanings, yes? Hopefully you understand that. Moving on, though. Okay, so conductors and insulators. So conductors in metal, some electrons can move freely through the metal, and we call that like the valence electrons. Others can be moved, but pretty much the valence electrons, they can move. When you bring a positively charged rod next to a metal bar, the free electrons move closer to the positively charged rod, leaving the other side with a deficiency of electrons. So here you go. So you have your positively charged rod, and it's going to attract the free electrons in that thing. That's important to understand. And now the opposite obviously is going to be true. If you have a negatively charged rod, so to speak, those positively charged protons are not necessarily going to move that way, but the negatively charged electrons are obviously going to be sort of pushed back the other way because opposites, similar charges repel. There we go. Ooh, I said I can talk. All right, so conductors, here we go. So imagine we have a small ball of aluminum foil and we take a negatively charged rod to it. And what would happen here? Well, the aluminum foil would obviously be attracted to it. And what's going to happen is those positive charges are going to sort of shift to well, not the positive charges, but the negative charges are going to push away, but those positive charges are going to be attracted to that on that surface of that thing. The metal foil ball then touches the rod and acquires some of the negatively charges from it. And what's going to happen then is it would actually kind of be repelled from it. So you'd have that part where it actually gets repelled from it. And notice, and this is important to kind of see, you can actually count them if you want. I think it should count up. Yeah. So right here you have 1, 2, 3, 4, 5, and then 1, 2, 3, 4. So you've got 9 total charges, and here's 1 left, and then 2, 3, 4, 5, 6, 7, 8, 9. Okay, so either I missed a 1 or I'm counting 1 wrong, but there should be the same amount of charges on there, because that conservation of charge. But it's going to pull those, so to speak, positive charges there. All right, so what we have here is an electroscope. I have seen these before. Once again, broken. I've seen a lot of broken science equipment. That's kind of weird. I've never actually bought one. I have seen one actually used in college once. And they're kind of neat. They talk about measuring amount of charge. It's a ball, very lightweight needle. That metal rod is connected to a pivot near the bottom of the large rod. And here what happens is the angle of deflection, so basically it bends, related to this charge on the electroscope, or the charge of the object. So you bring your object near. If you have the positive charge on the ball, some free electrons in the metal ball and the rod move to the bottom of the rod. To the needle, they repel. When the negatively charged object is moved, then the needle obviously will move the needle. After a negatively charged object touches the metal ball and then remove, the needle and rod have negative charged and repel. So, yeah, they're neat. Find it on YouTube. Sometimes you'll see a problem talking on here with a picture on it, so it's good to understand how they work. But basically, you've got that negative. When you bring that negatively charged object to it, the ball that's positively charged is so the negative charges are going to sort of force that thing to bend a little bit, and it's a good way to measure the amount of charge in a sense. I'm rambling. Moving on. Okay, dielectrics. So plastic, glass, and other non-metal materials do not have free electrons or any other charged particle that are free to move. So they don't have that ability to actually just move all over through the object. And that's important to understand. So here's a neutral atom with charge uniformly distributed, right? So you got plus, minus, all this good stuff. Now what happens is when a positively charged object is brought near the dielectric material, its atoms and molecules become polarized. So although they can't move, they sort of redistribute themselves. There is now a weak attraction between the charged objects and the dielectric material. Polarization also occurs when bringing a negatively charged object near a non-conducting material. So again, you get that polarizing effect. They don't. So in a conductor, they're actually going to physically shift. They're going to move. In an insulator or a dielectric, they're going to sort of just adjust, so to speak. So whereas in these could be a little bit more random, they're going to be adjust so that all the negative are on one side of each little part of it. So it doesn't actually freely move. It just sort of adjusts itself in its own little space. Electric properties of materials, conductors and insulators. Let's see here. Well, that was a horrible choice for animation. Material can be divided into 2 groups, conductors and insulators, or dielectrics. Both materials are composed of oppositely charged particles with a total charge of 0. In conductors, some of the charged particles can move freely. In dielectric, charges can only be redistributed slightly in the process called polarization. And we saw that before. The conductors, they can physically freely move inside and they can be transferred. But in a dielectric or an insulator, they can't move or be transferred. All they can do is sort of slightly adjust their rotation, or not their rotation, their position a little bit. All right, so this is important to understand. Electric charge is completely defined by the effects it produces. You cannot see electric charges. And this is a cool little system. This is what we call the solar system model of the atom. But understand that no one's ever seen this before. This is just a theory or a model that fits with our adjustment. What happens is these move so fast, they blur, and they create what we refer to as the electron cloud, which is what people see with electron microscopes. And we can measure certain things. We know that this is mostly empty space. We know that this is tiny. We know that there's a neutral side. We believe, by know, I mean can test and use models to accurately explain it, but no one's ever seen per se, but we can measure its effects. So we can't really see these charges. Again, these are models that fit the facts we know and fit all the experiments we have. And that's what we remember from the previous video. We talked about historic models and current models. But it's important to understand all we can do is measure its effects. All right, so is the human body a conductor or a dielectric? Well, as your hand approaches a positively charged cup, the free electrons on the surface of your hand and arm move towards it. So, if your hand touches the cup, free electrons on your hand transfer to the cup until the net charge on the cup is 0. So, tell me, conductor or dielectric? Conductor. Human bodies actually are conductors of electricity. We're not the best, but we are conductors. And it really ends up being a lot of the salt in our body because we're mostly water. Pure H2O is not a very good conductor, but water, because it usually will have ions in there and salt and stuff, becomes a very good conductor of electricity. Well, not very good, but good. All right, groundings. This is important to understand. And you may have seen around your house. Sometimes they're easier to spot than others, but there's this random pole just drove into the ground, and there's a wire attached to it, and that is a grounding wire. That helps people from building up charge. Building up either a positive or a negative charge. And grounding is important because it keeps you from getting shocked by your own appliances and things. So if a cup has a positive charge, negative electrons in the ground are attracted toward the cup, travel from the ground to the cup, cause you to become neutral. And that's why houses are always grounded. If they weren't grounded, the problem would be is you'd have charge build up on these electrical sockets, and once you plugged it in, you get a big boom, bang, bang, you're no good. So that's why we often ground things. So the wire provides a path from electrons from Earth toward the positive charge cup, and your houses are always grounded to prevent that from happening. So you might get a little shock, but if you plug something in, it shouldn't have a buildup of electric charge that basically would kill you. That would be bad, right? So that's grounding. This one's it's not as important. I'm just go over it real quick. Discharged by moisture in the air. If you leak a negatively or positively charged object alone for a long time interval, the object can become neutral, in part because of the presence of water vapor in the air. So you have a water model, and the net effect is obviously an electric dipole, so it sort of neutralizes it out. This isn't really that important, but we still put it in there because it's. I actually have no idea why I put it in there, but it's a good idea. Okay, properties of electric charge. So similar to mass, momentum, and energy, electric charge is a conserved quantity. And this is important. Mass is conserved, momentum, energy, these are all conserved quantities. Electric charge is also conserved. It changes in a predictable way in a non-isolate system and is constant in an isolated system. That's important to understand. So what happened before has to happen after. All right, so here's our practice make perfect question. This is, like I said, a shorter one. You have a foam, well, maybe not have said that. You have a foam rod rubbed with a felt and a small aluminum foil ball attached to a thread. Describe what happens when you slowly approach the ball with the rod and then touch the ball. Come on, pause if you need to. Go back, check your notes. The foam rod rubbed with the felt becomes negatively charged. When brought near the aluminum foil ball, the charge on that part of the surface of the ball becomes positive, so the negative charge is farther away than the positive charges. Hence, the aluminum ball is attracted to the foam rod. And that was shown in the beginning of the notes. Now, a little extra credit assignment if you want it. Shoot me a video on its learning. I'll put it on as extra credit of you doing this experiment. Foam rod, aluminum ball, rub it up. Good luck.